Hello friends, hope you all are fine. Yes, so today we are going to discuss about a special topic called Hamiltonian graph. It is a topic from graph theory. Graph theory is a fascinating branch in the mathematics subject. Hamiltonian graph is the name came after the mathematician Sir Hamilton. Well, these are some prerequisites to understand this topic today. We need to know what is a graph. Graph is a combination of two sets, v that is vertex set, edge that is an edge set, and we have one mapping which is called induced function, or we can say incidence relation from the set v cross v to the set E. Well, undirected graph means the graph where edges are not directed. Connected graph means there is a path between every pair of vertices. Simple graph means there is no loop and there is no parallel edges. Cycle in a graph means it is the sequence of vertices and edges starting from the vertex, ending with the vertex, and no repetition of vertices is allowed. Complete graph means every pair of vertices are adjacent to each other. That means there is an edge between every pair of vertices. So these are the terms that we are going to use in this particular session. Working towards Hamiltonian cycle. Hamiltonian cycle is a particular cycle in a given graph which includes all the vertices of the graph. A graph which admits Hamiltonian cycle is known as Hamiltonian graph. Sometimes a cycle is also known as circuit. In different books we have different terminology. Here I am adopting the terminology from the book called First Look at Graph Theory by Clark and Halton. So here in most of the sense we are going to use cycle word instead of circuit. Here I have written both the words just for your knowledge that cycle and circuit seems to be same. Well, look at on the example. Here one example on the 6 vertices is given. There are 6 vertices and 5 edges. Consider this graph. We are supposed to have a question that does this graph admit Hamiltonian circuit, or what will be the Hamiltonian circuit, or how can we trace Hamiltonian circuit? So again, look at the definition. Definition says that Hamiltonian circuit or Hamiltonian cycle is a cycle which covers all the vertices of the graph exactly once without repetition. And of course, once vertices are not repeated, edges cannot be repeated. So we can start with any vertex here, and we have to traverse along the edges of the vertices to cover all the vertices exactly once. Repetition of vertices are not allowed. So let us begin with any one vertex here. So I started with the initial vertex, and we have considered an edge, blue colored edge, and we are traversing through the edges of the graph to cover all the vertices. So one simplest way to construct one Hamiltonian circuit is gone like traversing the edges on the outer cycle. That is starting with the blue edges that we can see. We are traversing like this on the outer cycle, and it made through all the edges exterior to this graph, and we are coming back to the original vertex that we started with. That means it is a circuit, and of course it covers all the vertices. So it is a Hamiltonian circuit or Hamiltonian cycle. A cycle covering all vertices exactly once is Hamiltonian cycle. That means vertices are required to be covered, edges may be left out, doesn't matter. Here it's not necessary that all the edges are covered. So vertices are to be covered. That is the condition for Hamiltonian circuit. Now the next question is, can you have just one way to get the circuit? That means, can you have just one circuit only in the graph which covers all the vertices? And the answer is no. You may have more than one circuits. That means Hamiltonian circuit is not required to be unique. You may get more than one way to connect all the vertices exactly once and coming back to the same vertex again. So, what will be the another way to consider Hamiltonian circuit here? So let us consider the same graph, and let us start with the same vertex, and let us have another form of the Hamiltonian circuit. So starting with the edge, right from the first vertex, top of the graph, and we are traversing the blue line for the edges considered in Hamiltonian circuit. This first one, then let us go for the second in this sequence, then third one go to the diagonal way, and the fourth one go to the left, fifth one go to the down, and sixth one go to top. So we got another Hamiltonian circuit which covers all the vertices exactly once, and coming back to the same vertex. Circuit means obviously we have to come to the same initial vertex that we have started with. So this is a graph where we have shown two different Hamiltonian circuits. Now it may happen you get more than two. So depending upon the graph you can get different Hamiltonian circuits for the graph. Now what is main origin of this Hamiltonian circuit, or what is the original problem that is been having important role to work out with the Hamiltonian circuit, or to work out with this concept? So the Irish mathematician Sir William Rowan Hamilton originated this concept. The concept was started with actually a problem. Sir Hamilton has posed a problem that a person wants to travel 20 cities which are situated in a particular location, in a particular region, where the map is considered to be representing a dodecahedron. So in the map, the points, the vertices are cities. Vertices are considered to be cities, right? And edges means the roads connecting them. So we have one particular map connecting all the 20 cities. Every city is designated by a particular vertex, and if there is a road between two cities, then it is nothing but it is designated by particular edge. So we have a dodecahedron representing this situation, this particular map. A person wants to travel this 20 cities. Is it possible to plan a journey for that person to cover all the cities exactly once? No repetition of the city is allowed. And one more condition is you need to come back to this city that he has started his journey. So that's the problem. The problem is this: the person has to start his journey to travel all the 20 cities and coming back to the same city that he has started his journey. So is it possible? Is it possible to trace such journey? So the answer of that lies in a particular graph model. So considering a graph model, this is dodecahedron where the vertices are representing the cities and the edges connecting to them represents the roads or the traveling route. Now we are supposed to work on this, that a person starts with one vertex or one city, traversing around all these cities, that means going through all the vertices exactly once and coming back to the same city, that is same vertex. In other words, we can say it is a problem to find Hamiltonian circuit in this dodecahedron. It's a graph with 20 vertices and so many number of edges are there. We are supposed to cover only and only vertices, and that should be exactly once, and you should come back to the same city. It should be closed path. So working on this, again I'm traversing the Hamiltonian circuit by means of blue line. So we start with the topmost city here, and then a blue line is suggesting an edge which you are going to form to construct the Hamiltonian circuit. Going for next, so I'm getting little inside. Let us go inside to this, right, by the blue colored line. Next, cover the next vertex, very next vertex, then go again inside, then cover the pentagon which is completely inside this. So cover this pentagon by means of the edges, colored blue line. Now do not add edge here, do not consider this edge, otherwise this vertex will be repeated when you are going or going back from this, right? So this edge should not be included. Then we have to come out. So to come out, let us consider this next edge. Next, include all the vertices or the second level boundary. So we are considering again blue edges which cover the second level boundary. And now again we can't join the edge which is in the second level, so we'll have to get out from this, and then again joining this, traversing this blue line, we can reach to the vertex that we started. So this is the Hamiltonian circuit for dodecahedron. Again, yes, in this case the conclusion is that the person who wanted to travel 20 cities without repeating any city and coming back to the same city, that journey is obviously possible by means of this Hamiltonian circuit. Now we started with the topmost vertex. It is not necessary to start with this. You can start with any one vertex arbitrarily, and we can traverse along all the vertices and you can reach to the vertex that you started. Now the question is there possibility to have another Hamiltonian circuit? That means, is there any other travel plan which satisfy that original conditions? I'm leaving it for you. Try to get, if possible, try to get one more such Hamiltonian circuit in this dodecahedron. So that's a work for you. It's not at all difficult. We start with any vertex and traverse along all the edges and come back to the same point, same vertex again. So that is what Hamiltonian circuit for the dodecahedron. Let us go further. These are few examples where we are going to look about on Hamiltonian circuits. Likewise, the first example, like it looks like pentagon. It is a circuit. It's a cycle with 5 vertices. Right, in this circuit or cycle, we must start with any point, traverse through the edges, and you will come back to the same point again. So this graph itself represents Hamiltonian circuit. This graph itself is a Hamiltonian circuit. Right, and more or less we can say that there is no more Hamiltonian circuits possible for this. So this graph is a cycle on 5 vertices or circuit on 5 vertices. It has a unique Hamiltonian circuit, one and only one. In the second graph, you may get more than one circuit, right? Just traverse from one vertex and just connecting to different vertices and try to get whether is it possible to come back again. Means try to get a conclusion whether we can have a circuit starting with one particular vertex, traversing around all the edges so that every other vertex would be covered and come back to the same point. Yeah, here all the edges are not required to be covered, but traversing to the edges we have to cover all the vertices. Same as this third figure, we may try for this to get Hamiltonian circuit. So I want you to respond on this to get Hamiltonian circuits on this 3 graphs if possible. Yes, now the question is that, is it possible that every graph contain Hamiltonian circuit? For that, first requirement is to be connected graph. Why connected? Because we need a circuit which covers all the vertices exactly once. So a circuit covering all the vertices is always being a connected subgraph of a graph. And since it covers all the vertices, that graph has to be connected. If the graph is disconnected, then it will have more than one components. If you have 2 components, then if you start from any vertex from one component, then by considering traversing through edges, we can never be able to contain the vertices of second component. So the vertices of both the components cannot be covered by a single circuit. So for a disconnected graph, Hamiltonian circuit does not exist. So if you want the Hamiltonian circuit, we need to have connected graph. This is the first requirement. Like if you consider a graph which is not simple, say there are some loops, there are some parallel edges, then what? Then Hamiltonian circuit will not have any trouble. It's like if you consider parallel edges and if you have Hamiltonian circuit, then out of that parallel edges you can remove one edge and still Hamiltonian circuit would be present there. Same is if the graph has a loop, if you remove that loop, still Hamiltonian circuit would be present. Loop will not make any role into the Hamiltonian circuit. So if a graph is not simple, then we consider underlying simple graph, and that will represent Hamiltonian circuit of both the graphs, underlying simple graph and the original graph. So we basically go for connected simple graph. Now the question is, if you are given connected simple graph, and here of course we are considering undirected, that the edges are not directed. So when you are considering connected simple graph, is it possible for every connected simple graph that it always contains Hamiltonian circuit? Unfortunately, answer is no. It does not contain always Hamiltonian circuit, because to have a Hamiltonian circuit, first condition is the graph must have a circuit. Now if you take the example of tree, what is a tree? Tree is a connected graph without circuits. It's connected acyclic graph. Acyclic means a graph without cycles. That means tree is a connected acyclic graph. Since it does not assume any circuit, it can never have Hamiltonian circuit. So any graph without circuit obviously cannot have Hamiltonian circuit. So tree is an example which is a connected graph, simple graph, but it does not have Hamiltonian circuit. Now, if the graph is not a tree, what can you say about the result? If the graph contains a circuit, will it contain Hamiltonian circuit always? Again, answer is no. Look at the example. Look at this graph. This graph is having 5 vertices and 6 edges. If you start with any vertex here, and traverse along this, look, traverse along this, and when you start with one vertex anywhere, you have to come back to that part. See, we can see this vertex by means of 2 parts: left hand side triangle, right hand side triangle. So if you start any vertex from left side triangle, if you want to traverse and cover all the vertex, you have to move on to the right side triangle. And once you move to right side triangle, you need to come back, and when you want to come back, you have to pass through this middle vertex, and you have to pass through it twice, which is not true, or which is not possible. Hamiltonian circuit does not allow repetition of vertex. So traversing along this middle vertex 2 times is not possible, or it's false. That means this graph does not have Hamiltonian circuit. Even it is a connected graph, even it is a simple graph, even it contains circuits, even it contains so many circuits, right? But it is not covering, it is not containing Hamiltonian circuit. So that's a reason that every connected graph with circuits may not have Hamiltonian circuit, right? Consider another graph. It's a very special graph. It is a graph given by Tute, mathematician Tute, in 1946. It's again a beautiful graph. There are so many vertices here, and unfortunately conclusion is this graph also does not admit Hamiltonian circuit. So a graph may have Hamiltonian circuit, may not have Hamiltonian circuit, whether it's connected or not, whether it contains circuits or not, right? Fine. And yes, a graph which does not include Hamiltonian circuit is called a non-Hamiltonian graph. Graph with Hamiltonian circuit, it's a Hamiltonian graph. Graph without Hamiltonian circuit, it's non-Hamiltonian graph. Okay, now using Hamiltonian circuit, we can have one problem or one solution of a problem. Basically, this is a problem not to find Hamiltonian circuit, but this is a problem to find a number of Hamiltonian circuit in a very special graph. The problem is known as seating arrangement problem. And here with this problem, or we can say the solution of this problem, lies in counting the number of Hamiltonian circuit in a complete graph. A special graph is called complete graph. As just I have referred and I'm revising again, complete graph means a graph where every 2 vertices are adjacent to each other. That means there is an edge between every 2 vertices. Consider example of triangle. In a triangle, every 2 vertices are connected by an edge. So it's a complete graph. It has 3 vertices, so it is denoted by K3. If a complete graph has n vertices, then it is denoted by Kn. It's a very basic thing in the graph theory. You might be knowing this. right? So the question is, or this problem tends to the calculation of the Hamiltonian circuits in complete Graph-Kane. So let's see what the problem is basically. The definition of problem goes to, there are certain number of persons in a company. Here we have taken that number to be 9. There are 9 members of a company wants to meet each day for a lunch to discuss about the progress of the company. They decided to sit in such a way that every member should have different neighbor at each lunch. That means, that suppose you consider one person to be the boss among this 9 that I have in picture designated by the red color. Say red one is the boss, right? Another 8 members are there sitting besides each other. Now the problem, or we can say the situation, is such that the boss should have two different neighbors each day. Means suppose person 1 and person 2 are the neighbors on the first day, then in the second day it should be person 3 and person 4. Next day it should be person 5 and person 6. So the question is that if this kind of arrangement is required for the meeting in everyday lunch, then how many days this arrangement would be possible? That means how many days that boss will find different neighbors. That means how many days every person of this group will find different neighbors each day. That's a problem. What is the answer of the problem? Let us consider the mathematical formulation for using the graph for this particular situation. So the situation represented there can have a particular graph model. In a graph model, we have two components, vertices and edges. In this particular formulation, every single person is represented by a vertex. Every single member of the group is represented by a vertex. And if we have, suppose boss or say person 1 has the neighbor person 2 and person 3, then there will be an edge between person 1, person 3 and person 1, person 2. That means the edge joining two vertices will represent the adjacency relation, will represent the neighborhood relation, will represent the relationship of sitting together or sitting next to each other. So vertex represents the member, that is persons, and the edge represents the relationship of sitting next to each other. That is the graph model in terms of mathematical formulation of the problem. Now this is the situation. Right now I will just little bit make it different to understand, to represent, to learn it better, that the central vertex what we are taking here, it represents, let us take a boss. This is the central vertex representing a boss. Another 8 members I have arranged into this polygonal form, right, around the boss, polygonal form around the boss. Now what we are exactly doing to find the solution? What was the solution? What was the problem we are going to find is how many days the arrangement would be possible. The arrangement will be long last. So we are going to start applying the edges. Like if we apply one edge to a person 1 to person 2, that means person 2 is a neighbor of person 1 at the first day. Okay, so right now whatever the line, it is about to dark orange line I'm tracing, that means it is the sitting arrangement for the first day. If you consider like this, that means what? The central vertex has the neighbor, this one, the top one, and the top one has the neighbor the right side, right? So every edge will represent the neighbor, corresponding neighbor. So central vertex has neighbor this, that boss has neighbor the top vertex or top person, then the right hand side, then it goes to left side. So this is the next, person 3 is neighbor of person 2, next like this, right? This is the neighbor of this one, next, right, left one is the neighbor of the right one. So we are going to have a zigzag pattern For the first day arrangement, like this. That means when you consider a boss sitting in the center, it has two opposite corners who will sit beside to this boss at the very first day. So boss is going to select the top one and the bottom one to have neighbors on the very first day. Same way, we can have different neighbors on the first day. This is the first situation. On the first day, we have this kind of situation of the neighbors. Now, what about the second day? Second day, the neighbors must be changed. The same neighbors won't work, right? Now, next day, the neighbors of each and every person must be different. So let's say here, this top and this bottom, two persons were there. The neighbors, they were the neighbors of the boss that is sitting in the center. Now, the very next day, the neighbors of the boss would be changed. Right, the neighbor of one of the neighbor is changed. Now the neighbor is this one, which was not neighbor of the boss in the previous arrangement. Right, earlier the boss had the neighbors, the top and the bottom. Now the situation changed. So consider that this vertex or this vertex is adjacent to the central vertex. Next, this vertex is adjacent to this one. That means these two are neighbors now. Earlier they were not neighbors. Earlier these two were neighbors. Remember here in the case of Hamiltonian circuits or in case of the sitting arrangement, in every day every person will have exactly two neighbors, right? Because there are two persons sitting besides that. So every day arrangement, every person will have exactly two neighbors. So this way we are going to move onwards and we'll have second day arrangement. You see, it's a second day arrangement, and if you observe carefully, that the neighbors of each and every person has been changed. How easily we can approach to this? You see, in the first day arrangement, we started with the central vertex and we joined this one, the top one, and then we have gone to right, then left, then right, then left, and that way we have to reach to the last one, and then we have came back to the center. Now the same situation is being rotated. This line or this edge is been shifted here. That means it is rotated left side. Yes, counterclockwise rotation. Right, counterclockwise rotation. And so we have a new sitting arrangement by just rotating the earlier pattern counterclockwise one step. It is not essential to rotate counterclockwise. You may rotate it clockwise. So this edge would be onto the right side. Onto the right side it would start. Either counterclockwise or clockwise. Any one method we can prefer. So this is second day arrangement. Let us consider third day. Now see, this central vertex has first day neighbor as the top and the bottom. And the next day it is this two, diagonal, up and down. So these two cannot be neighbors now for this boss on the third day. So third day, this third one, yes, almost left side bottom, right? This should be the neighbor on the third day. So let's go on. Right, this is the neighbor on the third day, and again we are going to have the pattern like considering zigzag. We have started with this is the first neighbor of the boss, then go to right, this is the neighbor of this vertex or this person, then going for that zigzag pattern. This gives you another arrangement on the third day. So again, if you refer it, there are completely different neighbors at each day, and this is possible up to this third day. How differentness you can come out with is the different colored line are not matching to each other, are not overlapping to each other. If any of this different colored line is overmatched, that means we have the same numbers, which is not the case. So here there are no different colored lines overlapping to each other, right? So third day such an arrangement is possible. Fourth day, yes, fourth day, the boss has been neighbor to this vertex, has been neighbor to this one, has been neighbor to this one, has been neighbor to this other three as well. So only the left case is this one, bottom, left bottom. So at the fourth day, the boss would be joined with or neighbored with this vertex or this person. And again, going for that zigzag pattern, we can finish out with this fourth day arrangement. Again, if you closely look on this, there is no overlapping of different colored lines. So this is the fourth arrangement. Okay, so refer it one more time for the conclusion. The central vertex, that is the boss, it had earlier two different neighbors, top, bottom. In the second day, it was orange colored line. It was orange colored line. For the next day, it was green colored line. Two neighbors. So they are different from the earlier one. For the third day, it is blue colored line, which are different from this two, earlier two. And for the last day, we have another two, right? Yellow colored line, which is again different from earlier two. So every day we are finding different neighbors to the boss. And not only this, for every other person, this seems to be true. So every person in the group finds different neighbors at each day up to 4. Now, first day this was the neighbor, second day this was the neighbor, third day this was the neighbor, fourth day this was the neighbor. Fifth day if you go, then you have to go on this vertex and it has been already covered by orange line. That means it had been already member or neighbor of the boss. So won't be happening that on the fifth day you can't take this one as a neighbor because it's already taken. And the fifth day you can't take this one as the neighbor because it is already taken by the green line. So this cannot be neighbor on the fifth day. Even this cannot be neighbor on the fifth day as a different one because it has been covered on the blue line. And even this one cannot be the neighbor on the fifth day because it also has been covered. That means now after the fourth day we cannot find new neighbors for the boss and for each and every person. Now on the fifth day onwards, if they are going to get together for the lunch meeting, the neighbors will definitely be repeated, right? So what is the conclusion? If you go and if you look upon this now, I'm starting it from the beginning again. If you look on the ticks now and if you closely relate this by the graph, we have nine vertices in the graph. Look on this orange lines. It starts with the central vertex and it ends with the same. Next, if you go on traversing this, you can observe and find that this particular path is not repeating any of the vertices. So it is a cycle. This is a cycle. This route is a cycle. Next observation, it starts from the central vertex and ends with the central vertex. So it is a closed path. Means it's a circuit. It is a circuit. And the next observation is it covers all the vertices of this graph. That means it is a Hamiltonian circuit. Yes, it's a Hamiltonian circuit. So first day arrangement gives you first Hamiltonian circuit. Same way, the second day arrangement, the similar progressive work gives you second Hamiltonian circuit. Third day, it will produce third Hamiltonian circuit. Fourth day produces another fourth Hamiltonian circuit. And fifth day, we can't go further. That means there are 4 Hamiltonian circuits finally available. Up to 4 days this arrangement is possible. So 4 Hamiltonian circuits are available. And look the observations that we have gone through already, that every age is different from each other. They are not overlapping. That means they are disjoint ages. That means the Hamiltonian circuits are disjoint Hamiltonian circuits. They are not having any age common in this. They are not having any age common in this. That means if you have 9 persons designated by 9 vertices and if you go along 4 different days, then we'll get 4 Hamiltonian circuits which are age disjoint from each other. Now, very important remark, let us look upon the degree of each vertex. Degree, that you know, it's a very basic term. Degree of a vertex means number of edges joined with that vertex, simply. So if you are going to count the degree, let us count the degree of this one, top vertex. There are two greens, there are two blues, there are two orange, and there are two yellow lines. 2 plus 2 plus 2 plus 2. That means there are total 8 degree of this vertex. If you observe the next, again they are matching with 2, 2, 2 and 2. Every Hamiltonian circuit, when it passes through any vertex, it will contribute 2 degrees. Every cycle passing through vertex, cycle or circuit, will contribute 2 to the degree of that particular vertex, of the vertices from which it is passing through. So there are 4 circuits passing through all the vertices. That means every vertex has degree 8. Now there are 9 vertices, each has degree 8, and such graph has to be complete graph. A complete graph Kn is a graph in which every vertex has n minus 1 degree. So this is K9, complete graph on 9 vertices where every vertex has degree 8. So when you consider K9, complete graph on 9 vertices, then we have 4 disjoint Hamiltonian circuits available. 4, the number is 4. Please mind it and remember this. We'll be using this later, just now after this discussion. So here the conclusion is that the sitting arrangement what we described is possible for 4 days when 9 persons are there. Well, extending this result and starting with the bottom line, when you say Hamiltonian circuit, you must need a circuit. For just 2 vertices, we can't have a circuit for simple graph, right? Because for the circuit to have, we need to consider 3 vertices at least in a simple graph. If it is not simple, we can have parallel loop. That's fine. But right now we are considering a simple graph. Let us consider a simple graph. Then when you consider 3 number of vertices, 3 number of persons, then there would be just 1 circuit available. Joining them, simply triangle, right? There is only 1 circuit available, and therefore there is 1 Hamiltonian circuit available. Or maximum number of days for the sitting arrangement is 1. See, number of edge disjoint Hamiltonian circuits gives you maximum number of days for this sitting arrangement possible. So for 3 persons there is 1 circuit, and therefore there is only 1 Hamiltonian circuit. For 5 persons, how the graph will look like? It is K5. It's a complete graph on 5 vertices. So if you observe that, you will have a pentagon as an exterior boundary, and we'll have a star in the interior. Pentagon in the exterior, star in the interior. And if you just trace them, pentagon will give you 1 circuit, fine, and the star will give you another circuit. And pentagon and the star, they are edge disjoint. That means 2 edge disjoint Hamiltonian circuits are possible. That means maximum number of days for the sitting arrangement is 2. For 7, we can roughly try out by just taking knot and pen and just draw case 7 and just trace out what just I have demonstrated by means of the figure, and we'll get the conclusion that for the number of persons goes to 7, number of vertices will be 7, therefore number of edge disjoint Hamiltonian cycle goes to 3, and therefore maximum number of days for the sitting arrangement goes to 3. For 9, just we have worked out 4, and for 11 we can again go for analysis of K11, and it would have the number 5. Now what is the general number? For 3 persons there is 1, for 5 it's number 2, for 7 associated with 3, for 9 it is associated with 4, 11 is associated with 5. So just using this sequence and using just kind of observation, when the number of persons is n, any finite, then maximum number of days for the sitting arrangement is n minus 1 by 2, and that is edge disjoint Hamiltonian circuit. Okay, and one more observation that we can find is we have referred here number of persons to be odd number. We have not written even number right now. We have only odd number. For an even case, we are messed up with this. We are not getting proper remark or proper conclusion, right? So when we have an odd number of persons, then we do have this result. So by and large, by means of this work, by just observation and going for a sequence progression, we come to the conclusion that if there are n number of persons, that means if there are n vertices, then there would be n minus 1 by 2 number of days that sitting arrangement is possible, and each such arrangement gives you a Hamiltonian circuit for that kn. Okay, that leads to a beautiful theorem, that leads to a wonderful important result in the graph theory, that is for Hamiltonian cycles or circuits. That theorem states that for any odd number n, the number of edge disjoint Hamiltonian cycles in a complete graph kn with n vertices, of course, is n minus 1 by 2. And this number makes sense. See, we are counting number of edge disjoint cycles. Number of cycles must be in integer. We can't have half cycle or 2.5 cycles. So number of edge disjoint cycles must be an integer, and n is odd, therefore n minus 1 would be even, and even by 2 is again integer. That means this number makes sense. So Hamiltonian cycles, computation of that in a complete graph with n vertices, with condition that n is odd, it should be n minus 1 by 2. Right? So let us move on for the proof of this. One way I just made you explaining that sequence, for triangle it's 1, for K5 it's 2, for K7 it's 3, K9 it goes to number 4, and extending that at the end, when you consider number n, then it may go to the n minus 1 by 2 number. Now it is a complete proof, theoretical proof, graph theoretical proof, better to say. How the proof is going? We are constructing cycles by considering the vertices. So first of all, for Kn we require n vertices. So consider n vertices and arrange n vertices on a polygon on n sides. Number of sides will be same as number of vertices in a polygon. So arrange n vertices on a polygon, on the sides of polygon. So we have n-sided polygon at present, right? With n vertices, obviously. That polygon itself is a circuit in graph theory. It's a circuit. So and it covers all the vertices, so it is automatically Hamiltonian circuit. So the first arrangement, arranging n vertices on a polygon, gives you one Hamiltonian circuit. This is first thing. First Hamiltonian circuit or cycle we can get by just arranging all vertices on a polygon. What is next? What have you done when we have referred that sitting arrangement problem? What we have done? We started with a point with our vertex and we are joining them and we are making one Hamiltonian circuit, right? What is next? We have rotated it. Rotated counterclockwise. We have rotated counterclockwise. Now, when you have one pattern, by rotating it, we get another pattern. Fine. But the question is that what will be rotational angle? How much we have to rotate to get the second, to get the third, to get the fourth, right? So, what is exactly rotation? We have started with the top vertex and then we just rotated once out of 8. We have rotated once out of 8. That means the degree of rotation, the angle of rotation should be 360 by 8. Total polygon will have angle sum 360, right? Total polygon will have angle sum 360. We have rotated just one step. So there were 8 vertices in the problem. We have rotated it just once. That means there will be angle of rotation as 360 by 8, right? Now how many vertices we considered there in the problem? 9. There were 9 persons be seated in a round table to work out with that arrangement. The number of vertices were 9. Number of vertices on the boundary of polygon and a rotation was 8. So we have considered 360 by 8 angle for the rotation. So rotate the polygonal pattern that we have described initially. That was our first Hamiltonian circuit. Rotate it through the angle 360 by n minus 1. In that problem n was 9, right? In general, it is any n. So rotated by 360 by n minus 1, it gives you one more cycle. See, we have rotated only polygonal pattern. So polygonal itself is a circuit. It remains there. We are just having a rotation. Only rotation, nothing else. So circuit remains there, and we have a one rotation creates one circuit more. Right? So 360 by n minus 1 degree rotation creates one circuit. Consider one more rotation. Like this is the first original polygonal petal. This is one rotation, 360 by n minus 1. Another rotation, another angle 360 by n minus 1. So total angle is 2 times 360 by n minus 1. So second polygonal pattern will be obtained by rotating the original initial polygonal pattern by 2 times 360 by n minus 1 degree. Right? One rotation, another rotation. Again, by rotating to the same kind of angle, means the third Hamiltonian circuit can be obtained by rotating the original one, the first polygon petal, by 3 into 360 by n minus 1 rotation. First rotation, second rotation, third rotation, each rotation will increase the angle by 360 by n minus 1 degree. So at the step of third rotation, the total angle which is rotated is to be 3 into 360 by n minus 1. Now how long it would go? How long? How many times you have to rotate? Like in 9 we have considered 4 rotations, right? 1, 2, 3 and 4. 4 Hamiltonian circuits were obtained which were edge disjoint. Now in that case of n, how much rotations are possible? Here I have written it is to be n minus 3 by 2. See, now this figure will come across every time. So when you consider 9, the first rotation, second number, third, fourth, fifth, sixth. So in the rotation, you will have n minus 3 by 2 number in between from 1 to n, right? So we are collectively first doing n minus 3 by 2 rotations. First rotation give you 1, first Hamiltonian circuit. Second rotation give you second Hamiltonian circuit. N minus 3 by 2th rotation gives you n minus 3 by 2th Hamiltonian circuit. So we'll get n minus 3 by 2 Hamiltonian circuits by this n minus 3 by 2 rotations. Fine. At that stage, after n minus 3 by 2 rotations, at that stage, how many circuits we obtain? N minus 3 by 2 rotations gives you new n minus 3 by 2 Hamiltonian circuits, and one original polygonal pattern was there. That was also a Hamiltonian circuit. So it's 1 plus n minus 3 by 2 and the number goes to n minus 1 by 2. So at the stage of n minus 3 by 2 rotations, we already got n minus 1 by 2 edge disjoint Hamiltonian circuits. Now why not more? Why only n minus 1 by 2 will be the fixed number that we are having? And why we are not getting more than this? The argument lies in this way, that when you trace any cycle, any circuit, any Hamiltonian circuit, it will include all vertices and it will contribute exactly 2 to the degree of each vertex. Every cycle, incoming and outgoing, incoming and outgoing. So every cycle will contribute 2 to each vertex. And since every Hamiltonian cycle is covering every vertex, that means every vertex will have 2 degree due to one cycle. Due to one cycle. Now how many circuits we have traced out? N minus 3 by 2 plus 1, that is n minus 1 by 2. N minus 3 by 2 due to the rotations and one original polygonal pattern. So total n minus 1 by 2 Hamiltonian circuits we obtain. So that will contribute 2 to each, that is 2 times n minus 1 by 2. 2 times n minus 1 by 2 will be the degree of each vertex, and that number goes to n minus 1. Now how many vertices we started with? N, Kn. How many degrees there for each vertex? That is n minus 1. That means it is a complete graph. The graph completely is covered. A graph Kn will be formed by considering n minus 1 by 2 Hamiltonian circuits which were edge disjoint. Because after ending with n minus 1 by 2 Hamiltonian circuits, every vertex will have degree n minus 1. And since the number of vertices is n and every vertex has degree n minus 1, it should be a complete graph gain. So total graph is covered, so no more edges will be added which will be edge disjoint of the former one, right? So now when if you add one more rotation, it will be having edges to be repeated with earlier rotations or with earlier Hamiltonian circuits. That means we have exactly n minus 1 by 2 Hamiltonian circuits obtained in Kn. And of course they are edge disjoint because we are rotating the pattern. We are just rotating the neighbors, so we don't have same neighbors every day. So the obtained Hamiltonian circuits by this rotation of polygonal pattern will always give you edge disjoint Hamiltonian circuits. So hence the theorem is proved. So a beautiful result we have been through that whenever we consider any complete graph with odd vertices, then we'll have exactly n minus 1 by 2 edge disjoint Hamiltonian circuit. See, many Hamiltonian circuits would be possible, but here the term we are going to, restriction we are going to take is edge disjoint Hamiltonian circuits. Now general natural question lies upon when you consider complete graph with n vertices and n is even, what could be the number? What could be the result? Or is there any conclusion about that? But unfortunately, for complete graph with number of vertices to be even, we don't have yet any generalized result for number of edge disjoint Hamiltonian circuits. So hope you enjoyed this session. It was a beautiful theorem, and we have gone through two different things here. What is Hamiltonian circuits and counting Hamiltonian circuit in a very special graph called complete graph. So if you like this, subscribe to our channel, Abel Mathematics Club. Thank you for watching this video. Thank you all.